Today we will discuss radial equation in hydrogen atom. So we have some mathematical equations, mostly second order differential equation. Interestingly, nature is actually made of many of second order differential equations. So if we can solve it, that's good. But if you cannot solve it, still it is okay, as long as you understand the meaning of the results. Previously, we solved angular equation, and then the most important results are L is the orbital quantum number, or angular momentum quantum number. It starts from 0 and goes like 1, 2, 3 and so on. And then M is the z directional angular momentum quantum number. It could be minus L plus 1, and then goes up to L. And lambda for this angular equation to have any solution should be the same with L plus 1. Those are important results. So if you can understand this, then it's good enough. Okay. Now we put this into here, radial equation. So radial equation is now written again. Instead of lambda, we set like L plus 1. And here, still equation looks pretty complicated. So we set R to be the same with chi over R. Then this one round R is here, okay? Because large R is replaced by chi over R. Then if you take the derivative, then you get this. So we call this as the partial derivative. Then firstly 1 over R, take the derivative, then we have minus 1 over R square. And then 1 over R goes first, and then we take derivative on chi. So round chi, round R. And we multiply it by R square. Then we have minus chi plus R round chi round R. Then we take derivative as shown here. So we go one by one, like 1, and then we multiply by R square and take another derivative. Then we have this one. Then minus round chi round R. And this one, again we have partial derivative. So R becomes 1 after derivative. So round chi round R plus R round square chi round R square. And then we multiply by 1 over R square, this one. Then we have this one. Because minus plus part, they subtract with each other. Then we multiply it by 1 over R square, right? Then we have this 1 over R round square chi round R square. Okay. So it is replaced by this one, and then the others just the same, and large R replaced by chi over R. Alright, so we rearrange this equation, like we multiply both sides by small r, right? Both sides. And we have And also, yeah, this one, yeah, if you want, you multiply by minus h bar square over 2m. So there we have this equation. And if you look at this, this equation depends only on r, okay? So now it is one-dimensional, yeah, problem because we only have one variable. And then to look at the structure, okay, we saw this structure many times, minus h bar square over 2m, round square something, round something square, in many one-dimensional problems. And this one, there's a potential and then additional part, so we replace this as like this, V effective, okay? This equation looks like that of a one-dimensional potential case with V effective. So if VR is given, we can solve this radial equation. And most important problem is the Coulomb potential problem, where VR is proportional to 1 over R. And that is actually hydrogen atom problem. Hydrogen atom problem we'll discuss. Yeah, hydrogen atom is the lightest atom. But still, now we need to consider two particles at least. One is proton, which is supposed to be very heavy, so it doesn't move. The other is electron. They are under Coulomb attraction. Here we need to consider two particles. So the Hamiltonian is now split into two different parts. You can consider proton to be particle 1, electron to be particle 2. Then you need to consider the kinetic energy of particle 1, and then kinetic energy of particle 2, and then potential energy. So we only solved one particle problem before. Now it's two particle problem. So it looks a little bit complicated. But we can note that proton is very heavy. So mass 1, M1, will be extremely large. We know proton is 1800 times heavier than electron. So relatively, we will ignore this, okay, like this. And then their potential energy is only proportional to their distance, okay? So for example, the x1 is set to be 0 because proton doesn't move. Relatively, it is mostly stationary, and electron moves quickly. So it is actually a function of electronic position only. And then we can go through some mathematical process to make it more systematic, as shown here. So here you will change the coordinate based on large X and small x. The mathematical procedures are a little bit complicated. We'll skip that part, but if you can understand the meaning, still it is good enough. So most of semiconductor classes actually discuss these issues because we need to care about Coulomb attraction. Coulomb attraction means there is at least, two particles separated, by a distance of r. So this is actually important problem. here in this case, large X, the center of mass coordinate, defined like this. M1 x1 plus M2 x2 over M1 plus M2. And X is the relative coordinate, x1 minus x2. So to make it simple, we are only considering X, not Y or Z for now. But in reality, actually it will be replaced by that three-dimensional coordinate. But here, instead of those dimension, we consider center of mass and relative coordinate. And potential is only depending on the relative coordinate. So if we look at the structure, this one is the kinetic energy part in center of mass coordinate. This will include both kinetic energy and potential energy. Then you will have confinement energy. This is similar to our free particle problem. It doesn't have confined energy. So in quantum mechanics, it doesn't generate that interesting issues. We mostly care about this part. Okay, relative coordinate. And first part can be replaced by HCM, Hamiltonian of center of mass. And second part is HREL, so Hamiltonian of relative coordinate. And the mass, large M, is M1 plus M2. It can be named as mass of the center of mass coordinate, and actually M1 proton mass, M2 electron mass, so you can also say mass of the electron and proton. It will be very heavy, right? And reduced mass is mu. Actually mu is the reduced mass. And to calculate mu, you need to consider this, 1 over mu equal to M1 plus M2. If you look at the structure again of this guy, we'll focus on this. This will be very small, and it only has the kinetic energy part. So this one matters most in this class. And here we note that we only solved single particle problem, one particle problem previously, and there was a mass, and that mass mu is now replaced by reduced mass, and others are just the same. Okay, so if you calculate mu actually from this, you can easily see that M1 plus M2, and then M1, M2, like this. So key issue here is when two particles with mass 1 and mass 2 are coupled by Coulomb attraction, then the problem will be now changed, a single particle problem of mass mu. Okay, and the mass mu is just replaced like this. Okay. When you have electron and proton, then in this case, because mass m is extremely heavy compared to mass 2, so by comparing this m1 and m2, you will ignore this part. Then m1, m2 subtract with each other, then mu is just the same with m2. So this is like electron problem, but now we use this Coulomb potential. So even though it looks complicated, if we understand the structure, we can make it simple. And now the radial part of Schrödinger equation for the reduced mass, because we need to consider hydrogen atom. So again, it was mass m previously, but now we need to consider two particles. That we just replace the mass m by reduced mass. Others just the same. Okay, that's the way we solve this very complicated problem. You need to study quantum physics of physics department for 1 year to understand this. But usually for semiconductors we don't have time for those details. There are way more to consider in terms of application, so I'll skip most of those tedious quantum physics part and explain the meaning, and then we accept the result. So everything is just the same. When we went through the procedures to make radial part simple, and then the mass m is just replaced by mu now. Okay, so if you know the meaning of reduced mass, things are simple enough, even though it is two particle problem now. This. We can simplify above equation, then solve differential equation called Laguerre equation. You can study how to solve Laguerre equation in undergraduate course, the differential equation course. Again, the large R is replaced by chi over R as we discussed previously. Then you will get this, and you need to solve this. It's actually already very complicated, so we will just accept the final result. Okay, and the solutions for this, then you will get the mathematical structure of chi. Okay, then based on that you will get the mathematical structure of R. Right? Then energy En, that's the important part. So it has some material parameter. Like if you consider a hydrogen atom, then you will only consider epsilon 0. But you can also extend these ideas into semiconductor structures. Then you will change this epsilon 0 by epsilon. That is called as dielectric constant. It is usually 10 times larger than epsilon 0 in semiconductors. And mu, it is almost the same with effective mass because proton mass is too heavy. So we now changed it into Me, electron effective mass. Z is the atomic number. Hydrogen has the atomic number of 1, right? Helium has 2. So you can apply this idea into different atoms too. So at least for hydrogen atom, you can set Z to be 1. And there is principal quantum number n, and n starts from 0, from 1, 2, 3, and so on. And other parameters are all arranged to be same with alpha. Alpha is a constant, but you can calculate that. You will see the meaning later. But, if you calculate all of them, for example, this one, now you just consider free electron mass in the case of hydrogen atom, okay? Because it doesn't affected by the band structure of semiconductor. Then you will get this number, 13.6 electron volt. Okay, right? And you learn this before in chemistry, course. It's called as Rydberg energy. Rydberg energy. It was measured by some experiment. So even without quantum mechanical calculation, people knew that there is certain energy like minus 13.6 electron volt. This is sort of the bound energy between electron and proton in hydrogen atom. And as we increase n, energy will be changed. And also from Raguer polynomial we can get the R. And R depends on principal quantum number n, and then angular momentum quantum number L. For example, if n is 1, L should be 0. That's it. Then you don't need to calculate this, you just accept this and use it. And here A0 is given here. So this is actually the scale of hydrogen atom radius. And we call this as Bohr radius. So if you know the meaning still is good enough, you will see Bohr radius many times in research papers. Now 20, it means n is 2 and L is 0. Different angular momentum quantum number will lead to different wave function shape. When n is 2, L could be 1. Okay. There are two different kinds. Okay. And large n, and it depends on n and L. It is normalization constant. It might look complicated, still it is okay. It is already listed in your tables always. And if you remember the structure of energy, it is good enough. So the energy was given like this, and R is given here, A0 is on the order of 0.5 angstrom. Okay, it is called as Bohr radius. Okay, so L was angular momentum or orbital quantum number. It ranges from 0 to n-1. n-1. Okay, it is important. If n is 1, L could be 0. L should be 0. N is 2. L could be 0 or 1. Energy doesn't depend on L. Okay, it only depends on n. Eigenfunction R and L depend both n and L. Okay, there is L dependence. When n is very large, energy level separation, which is 0, I mean, because it is inversely proportional to n square. So if we think about like n, this n could be like 100, and then next level 101. The energy separation is extremely small, so it's very hard to recognize their difference in experiments. Then we can say energy level separation reaches 0. When energy level separation is almost 0, they are overlapped very closely, then we use the concept of density of states. It's one of the important topics of semiconductor studies, and it is equal to the number of states per energy level. So because they are closely packed between different energy, let's say this is energy, there are many different energy levels mixed up. So at certain energy E0, for example, we can count how many energy states are there because they are very closely packed. How many states are there? We use G. So that is the number of states per energy interval. At certain energy E0, how many energy states are there? It is named as G. It is density of state. The energy eigenvalues are also called as Bohr energy because Bohr mathematically, what should I say, proposed this structure even without quantum mechanical calculations, which was too difficult already. But like 100 years ago, it was even more difficult to calculate this. But by his own intuition, he could induce rather simple structure of the energy, and that's why it is called as Bohr radius. Yeah, he got the Nobel Prize in this way. Full wave functions for hydrogen atom. So we'll just go over this. Even though you won't have that many cases or chances to see this again. But this eigenfunction, which is actually R, the radial part of solution, and Y, the angular part of solution, they multiply together, then you will have this. And this hydrogen atom problem that is formed by Coulomb attraction between proton and electron. So people don't use hydrogen. Well, I mean, maybe if you consider the hydrogen engine or some other related energy issues, then you need to consider this, the structure of a hydrogen atom, maybe for your research. In my case, if I study semiconductors, one of the most important particle you need to use is exciton. In simple term, we just use X, but full name is like this, exciton. Exciton is a particle formed by an electron and a hole, okay? Instead of proton, you have the hole, and the other is electron. They are under Coulomb attraction. You will see this particle many times in semiconductors. And this is almost the same structure with hydrogen atom, with one exception. Hole is much lighter than the proton. So we know we can calculate MH, hole effective mass in semiconductor, and ME, electron effective mass in semiconductor. Then two particle problem we have. So things will be complicated, so what we can do is we calculate mu, reduce the mass first. So this mass is now called as exciton mass. Okay, there is like this. Okay. So the reason I'm explaining this is, even though I don't need to know hydrogen atomic eigenfunctions, still I might need to use these structures to understand exciton. Especially exciton concept still survives after a long time, because the new materials like two-dimensional nanostructures, like a transition metal dechalcogenide, has extremely strong exciton effect. And all the important semiconductors such as silicon, gallium arsenide, gallium nitride, they all have strong exciton effect. So if we want to use those semiconductors, you need to understand exciton. And that exciton has the same structure of a hydrogen atom. So sometimes you need to understand this wave function structure, then adapt some of the parameters to be suitable for excitonic description of semiconductors. So I hope you understand my emphasis on exciton. So we will discuss exciton problem again later on in next class. But today, let's just go over the basics. Okay. Most importantly, we know quantum numbers. Please remember, you should understand the meaning of these quantum numbers. There are three different quantum numbers: N, principal quantum number; L, angular momentum quantum number; M, g-directional angular momentum quantum number. When N is 1, L should be 0. When L is 0, M should be 0. There's only one state. And when N is 2, from here to here, L could be 0 or 1. When L is 1, M could be 0 or plus minus 1. So you can see that there are 1, 2, 3, 4. So we see there are 1, 2, 3, 4. 4 different states. Okay. When N is 3, L could be 0, L could be 1, L could be 2. Right? When L is 1, M could be 0 or plus minus 1. When L is 2, L could be 0 or plus minus 1 or plus minus 2. Okay? So how many states are here? There is 1, 2, 4 two different states. 1, 2, so 4, 5, and then 6, then 8. Right, so and then this state, when N is 1, then L is 0, and M is 0, it is called as 1s state. So 1 is from N, principal quantum number. S is from L. When L is 0, the chemist call this as S state. Okay. Again, when n is 2, L is 0, then it is 2S state. When n is 2, L is 1, it's called as 2P. n is 2, L is 1, then it is 2P. So this name is depending on n and L, right? Likewise, 3S, 3P, and then 3D. Okay. When L is 2, we call it D state. Okay. So you need to remember this. Okay. Because it's often found in research papers. These are the wave functions. First one is N, second L, third M. Okay, so wave function depends on all those three quantum numbers, and these are the eigenfunctions. I don't remember those. I just use the structure to understand the exciton sometimes, only sometimes. You will see some of this wave function shape in your some serious mathematical research papers. Okay. Before I stop this, let me again count the number of states for each n quantum number. We have one state here, and here we had 4 different states. Here we actually have 1, 2, 3, 4, 5, 6, 7, 8, 9. So actually it was 9 different states. So, but please remember that the energy is depending on n. Okay, only n. So here you have one quantum state with certain energy E1. Okay, here you have 4 different states with certain energy E2. Here you have 9 different states with the same energy E3. Okay. Yeah. So this energy shared by 9 different states. So we call it degeneracy. Degeneracy means how many states are there for certain energy value. So when n is 1, the energy is minus 13.6 electron volt per hydrogen atom. There was only one energy state. Then degeneracy D is 1. The lowest energy state it is, so we call it ground state. The lowest energy state is named as ground state. Then when n is 2, energy is fixed like this. There are 4 different states. So 4 first excited state. Then D is 4. Okay. The degeneracy is 4. For the the second excited state or third state when n is 3. There are actually 9 different states. So 9 second excited state sharing the same energy. And then we have d equal to 9. So we can find that d is the same with n square. N is the principal quantum number. We are ignoring spin. So we didn't discuss spin state before, so let's skip that part. Okay. For the references, just for your reference, for your possible future research, then you need to consider sometimes probability, density. We know psi square is the probability, and we know the normalization condition because probability integrated to be 1. So we apply this idea into spherical coordinate. Then psi square integrated in volume, okay, then you will get 1. Okay, and here you have not only R dependence but zeta and pi dependence. It is rather complicated, but if we don't have zeta or pi dependence, if they are equal with any zeta or pi variation, then if there's no zeta pi dependence, then the probability p, so could be changed like this, infinity, let's say probability, which is a pure function of r, so it means we already integrated zeta and pi, okay, already integrated. And we only care about R dependence because R dependence is most important part. So then this PR can be written like this. P is the probability density. And you can get average, most probable radius, and width. And most probable radius is when dp dl is equal to 0. Then from this equation you can get r, right? Certain value. Okay, that r0 is most probable radius. And average, yeah, mathematically written like this, or r bar. Okay. Then this one actually is like this. Same with R, PR, DR, just for your reference. So you won't get any the homework problem or the final exam problem related with this, but you will see this only in research papers. Okay, and with delta R, this is the same with the uncertainty, and it is defined by square root R square bar. So we take the average of R square and then minus R bar square. So we take the square of average radius, right? That's it for today.